I'm Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Infinite. We'll look at a mathematical construction called the Cantor set. It's an early example of a fractal. See the episodes Chaos Game and Mandelbrot set for more. And here we will explore the almost paradoxical collection of properties of the set, along with a surprising and important application in digital communication. To construct the set, start with a line segment of length 1. Divide that segment into 3 pieces and throw out the middle third. You now have 2 segments. Repeat the process on them. Divide each into thirds, throw out the middle thirds. Repeat the process on the 4 intervals that remain, and keep repeating forever. The Cantor set is what's left. Well, you might think that basically nothing is left, and you'd be right. It's unlikely, but you might think that there's as much left as you started with. But this is also right. So how can the Cantor set be nothing and everything at the same time? Let's find out. Mathematically, you can start with the interval 0 to 1, throw out the middle third from 1/3 to 2/3. You now have 2 intervals, 0 to 1/3 and 2/3 to 1. Both of those, by the way, include their endpoints. When you divide 0 to 1/3 into thirds, you have 0 to 1/9, 1/9 to 2/9, and 2/9 to 3/9. Throw away the 1/9 to 2/9, leaving 0 to 1/9 and 2/9 to 3/9. On the back end, we're left with 6 to 7/9 and 8/9 to 1. And keep going. So what's left? Well, we started with a segment of length 1. How much length is left? After one step, we have 2 segments of length 1/3, so 2/3 total. After the second step, 4 segments of length 1/9, so that's total length 4/9, or 2/3 squared. You can go through the details and show that the third step has length 2/3 to the third. Taking this process to infinity, with larger exponents, we have length 0, nothing left. Except that there are clearly points left. The endpoint 0 will never be removed, nor will 1 or 1/3 or any of the other endpoints. A change of viewpoint will let us see exactly which points are in the Cantor set. Think of those first 3 intervals as being labeled 0, 1, 2. We're throwing out the 1. The 3 intervals from 0 to 1/3 we can label 0, 0, 0, 1, and 0, 2. We'll throw out the 0, 1. Similarly, from the 3 intervals 2, 0, 2, 1, 2, 2, we throw out the 2, 1. Can you see what's happening? If we keep up the 0, 1, 2 labeling, we always throw out the intervals containing a 1 from the middle. We keep the left piece 0 and the right piece 2, but toss the middle piece 1. So after step 3, we would have intervals 0, 0, 0, 0, 0, 2, and so on. 8 intervals of length 1/27. Any point with a label containing only 0s and 2s is in the Cantor set. And there are an infinite number of ways to string together 0s and 2s. In fact, the infinity associated with this count is the same level of infinity associated with the original interval 0 to 1. In this sense, there are as many points as we started with. Well, we can see that endpoints will always be in the Cantor set. We're only removing middles. Is there anything else left? Well, hard to see how there could be since the set has length 0. But the labeling process above lets us see otherwise. The endpoint 0 would be labeled 0, 0, 0. It's always on the left side of a split. The endpoint 1/3 would be 0. It's on the left of the first split, but then it's always on the right of the next split, so 0, 2, 2, 2, the 2 repeating. The far right endpoint, it's always on the right, so 2, 2, 2, 2 repeating. All endpoints have labels that end in either an infinite string of 0s or an infinite string of 2s. Well, think about this. If you make up an infinite string of 0s and 2s, randomly, no 1s, you'll be describing a point in the Cantor set. If you do this several times, how many of these will have an infinite repetition of 0s or 2s at the end? For true randomness, basically none, right? And that's the proportion of endpoints in the Cantor set. Almost none. So where are those other points? Sorry, about the best I've got is that's a good question. Well, let's lighten this up a little bit by thinking about an application. As described in the excellent book Chaos, in 1960, Benoit Mandelbrot was a mathematician working at IBM when a problem crossed his desk about transmission errors. Testing communications networks revealed bursts of errors where a bit that was supposed to be a 1 came through as a 0 or vice versa. Engineers were unable to track down the source of the errors. Mandelbrot, attuned to mathematics such as the Cantor set, looked more closely at the timing of the transmission errors. In a period of time with a burst of errors, he zoomed in on the time axis and found that it still looked like periods of calm with small bursts of errors. Zooming into smaller time frames, the pattern remained of several intervals of error-free transmission interrupted by some bursts. The errors could be accurately then modeled by a process like the Cantor set. Well, assuming that Mandelbrot was correct, what good does this do us? Something this chaotic, but with this much regularity, could not have been caused by somebody spilling a Pepsi. It had to have a natural, non-human source that could not be controlled or drowned out by boosting the amplitude of the transmission. Instead, check bits were added to the transmission to allow software to identify and often correct the inevitable transmission errors. It's often true that if you understand how a process works, then you can control it. The fractals that Mandelbrot and others found in nature are complicated and fascinating mathematically, but they also have opened the door to advances in cardiology, electronics, computer graphics, and many other areas. The Nova video, Hunting the Hidden Dimension, beautifully illustrates many of these applications.